Hi, this is a video for compiler design, COMP442 and 6421. This is for week 7, slide set 8.5. In this video, we're going to show how you do AST generation using some very concrete examples. Let me share the screen here. Okay, let's do this. So, there are two examples. Let me set my things up, my cursor. Yes, okay. There are two examples. There used to be one example. For those of you who saw the slides before, there was one example. I added one. Both of the examples are heavily related to the grammar that you have in the project. So it's very pinpointed. If you're trying to figure out how to do the AST generation, that's probably going to be the, practically speaking, in the project, it's probably going to be the most useful video. Okay, so there are two examples again, and one of them is to generate an abstract syntax tree for a variable declaration. So variable declaration here is using the let syntax. So saying, for example, this is the example I'm parsing here, let v colon integer 23 semicolon. That's essentially a variable of type integer named v, who is an array of 2 by 3 integers. So if you parse using this grammar here, so that's a variable declaration here, which is using type, which can be integer, float, or ID, and is using also array size, which is essentially repetition here, right? Recursion, that is enabling you to create a list of a integer literal between square brackets. Okay, so if you use this grammar here and you build a parser that parses this stream here, then you're going to come up with a parse tree like this. You have a variable declaration, let ID colon integer, and then the array size 2, 3 between respectively square brackets, and then semicolon, right? And then the end of the list here, which is going to become important as we see when you generate the AST. Now, what's not interesting with this tree, note that this is a parse tree. This is the parse tree resulting from using this grammar. As you build a parser that implements this grammar, this is what the tree that the parser is going to figuratively build as it is executing. Now, what we want, or what we don't want with this parse tree, is that, for example, to have nodes that don't carry any semantic meaning like let or colon or semicolon or the square brackets here, or even the epsilon here, meaning the end of the list. These don't carry meaning that's going to be important to have when you use the tree as an intermediate representation later to do the semantic analysis and the code generation. So we want to somehow, as the parsing process is running, we want to somehow don't include these things that we don't need. If there would be also, if we would be using rules here that have been a result of a transformation of removing a left recursion, which would result in having the tree being stretched apart by example, the result of removing left recursion, then we also want to repatriate, for example, both of the operands of a plus or a times operation under the plus or the times node, as we saw before. Same thing will be used actually to do this kind of transformation also. So not only you want to remove things, you want also to reorganize the tree so that all the information that belongs below a certain semantic concept, the nodes are all below in the AST. which it is not sometimes in the parse tree if you apply transformations to your grammar. Okay, so this is the grammar, this is the parse tree, this is what we are parsing in this example. Now, as we saw in class before, what you want to do is to somehow transform your grammar into some kind of attribute grammar. So essentially what you're doing here is you identify what are the semantic concepts that are related to this particular part of your grammar. So for example, in this particular subgrammar here, so we have atomic concepts. So for example, the name of the variable is the ID, which is an atomic concept, whereas the integer, which is the type of this variable, is another atomic concept that cannot be broken down in other concepts. And then each of the integer literals, which represent the size of each respective dimension of the array, in this case it's an array, are atomic concepts. And then you have to identify if there are some composite semantic concepts. In this case, we have the array size. For example, 2, 3 is the respective dimensions of all the dimensions of the array that is being declared. Whereas a variable declaration contains 3 subordinate concepts, which are the name, the type, and then the array size, if there's one. In this case, there is. So you identify what are the atomic concepts. That's going to tell you what are the leaf nodes that have to be created in the process of creating the AST. Then you identify the composite semantic concepts that are going to be created or that are going to correspond to subtrees that you create as, again, that are basically going to aggregate semantic information with the nodes that are under this composite semantic concept. They're subordinate semantic concepts of this composite concept. So essentially what you do is you define one semantic rule for each of the atomic semantic concepts. Here I noted them in green. So for example, when you have you create the semantic concepts for the name of the variable, this is an ID node that you are creating, a leaf of the tree, which is an ID node. Then when you create a semantic concept for the type, then you create an ID node, which is type. Then when you create a node for this integer literal here that represents the size of one of the dimensions of the array, then you create another atomic concept. So you create a leaf here, a leaf node. Then of course, eventually you're gonna insert these semantic actions into the right-hand sides of your rules, of the grammar rules. Then for each of the composite semantic concepts, you create another semantic action. This one, not only it's creating a node, it is also, of course, these semantic concepts, the point is that they have children. So these children, if you remember when I explained how this works, it's basically using a stack, a semantic stack. So it's assuming here that when you create nodes, they are actually pushed onto the semantic stack. So when you call create leaf, it creates an AST node and pushes it onto the semantic stack. What these rules here, the rules that correspond to the semantic, composite semantic concepts, what it does, actually, it pops from the stack a certain number of nodes, one for each of the children of this composite semantic concept. It pops all the children from the stack and then creates a new node and then elects all of these 3 nodes in this case as the children of the new node, in this case, a variable declaration node, and then creates a subtree and then pushes back this new subtree onto the semantic stack. Same thing goes here for the array size. So here in this case, what's going to happen, and that's where the epsilon here comes into action. Thing is that the array size semantic concept may have n number, an infinite possibly an infinite number of subordinate concepts, because you can have any number of dimensions in your array. So you need to have some kind of marker to actually push onto the stack to signify this is the end of the integer literals that have been pushed onto the stack. Okay, so that's why you need to have this push epsilon here. So you first push epsilon onto the stack, then you push all the integer literals. So eventually, as you will call this create subtree here to create the array size node here, then it's going to read a pop from the stack nodes until it finds the epsilon node that was pushed first, hence at the bottom, towards the bottom of the stack. So that's why I have here pop until epsilon. So you see here that I have pop, 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 because there's exactly always 3 children to a variable declaration node. And then for array size, I have pop until epsilon, because I can have any number of children here. How do I know when to stop? I actually push an epsilon node onto the stack before I start pushing all the integer literals onto the stack. Now you might want, so that's why you have these atomic semantic concepts here, which are in green, and the composite semantic concepts that are in red. Now you might wonder, what are these numbers here? These are actually, because when I will describe later here, as I will explain here. So when I push nodes onto the stack for readability here, I basically give them a number. So that's the first one I push onto the stack, 2, 3, 4, 5. Eventually I pop 4 and 5 and 3 here, and then I push another one, which is now 6. Okay, it's basically just to make a correlation between, make a relation between what is shown here and what is on the AST. Okay, so that's what these numbers represent. Now then, what you need to do, now that you have your semantic actions, which are related to establishing what are the atomic semantic concepts, as well as the composite semantic concepts that relate to this part of the grammar. Then once you have created all of these semantic rules, then you need to know to figure out where you will actually put them inside of the right-hand sides of your grammar. Now, for example, let's start with this one here. So V1 here, what it does is that it creates this ID node here, which is the name of the variable. Of course, the name of the variable is parsed here. That one is easy. So after you've parsed this ID here, then you insert your semantic action here. So that it will create this ID node and then push it onto the stack. So that's where, for the atomic insertion in your grammar of the atomic semantic actions, or semantic actions related to atomic semantic concepts, you insert them in the grammar right after where this the terminal symbol that corresponds to this atomic concept has been successfully parsed. Okay, so that's why here my V1 is actually, that corresponds to this ID node here, is inserted here after ID. What are the other ones for type? So you see that after I have successfully parsed the type, which is after either of these here, then I insert my semantic action here. So after a successfully parsed integer or float or ID, I create the type node and I push it onto the stack. So that's going to be happening here. Now I could have put type here, but if I do this, then keep in mind that's probably type would be used somewhere else in the grammar. Okay, so if you want this to work in all occurrences of type, then you probably better put your semantic action here rather than put it here. If you put it here, then you have to remember to put it after any other occurrence of type in your grammar. Okay, so you see that there's different ways of doing this. There's no one single correct way of doing it. You have to figure out a way so that it works together. Consistent way that makes it work together and consistently for all cases. Okay, so for the epsilon. So what is my epsilon? My epsilon is the marker I will push onto the stack to signify this is the beginning or the end of my list of sizes for my array size, the dimension size, the size of each dimension. So when do I start parsing my array size list? It's actually here. So here, array size repetition is this thing that is generating each of my integer literal nodes. So that's before I start inserting these here or parsing my integer literals. I actually put this semantic action here that is creating this epsilon node and then pushing it onto the stack. So that's my marker to signify later on when this one is going to take effect, it's going to pop until epsilon. That's my marker that I just put there to make sure that I'm going to pop until what I just inserted now. So then I parse array size repetition. And then you see here that after I would have successfully parsed array size repetition, which is going to be the repetition of parsing each of the elements of the sizes of my array, then eventually I'm going to call A3 here, which is going to create my array size subtree. But before that, I need to insert into the stack each of my nodes that represent the individual sizes of my array. So you see that here I'm creating a node. My A2 rule is actually creating my node integer literals, these two here. So after I successfully parse one of the integer literals, I call my E2 semantic action, which is creating one leaf node for this particular size, this one and then this one, and then pushes this node onto the stack. So that's it for my leaf nodes. So you see that, as I just explained, after I will have successfully parsed this array size repetition, I would have inserted in my stack all the sizes that I have successfully parsed. So that's why when this is finished, then I will come to this rule here that is going to actually process this entire subtree here. So how is it going to do it? By actually popping from the stack nodes, which will be nodes that represent the size of the array, and I pop until I come onto the epsilon node, which I have inserted here. And then I create this array size subtree, and I elect each of the size nodes, the leaf nodes that represents the size of my array as children of this subtree. And then now I have this subtree here. The other semantic action to create a composite semantic concept is for my variable declaration. For this one, it is essentially assuming that there is 3 nodes upon the stack, which would be respectively the ID, which represents the name of the variable, the type of the variable, and then an array size node. If everything works correctly, it is going to be what I'm going to have upon the stack. Of course, the problem here is that if you don't insert your things in the right order inside of your rules, or if you forget one pop or you put one too many, of course, your stack is going to get corrupted and it's going to go haywire, right? So that's one of the difficulties of doing this. It's important that you spend some time, try to do things systematically, as I'm just explaining now, to figure out, what are my semantic actions, atomic, composite, semantic concepts, atomic, composite, what are the semantic rules, where should I put them, and that you somehow do this systematically and verify it as you go before doing your implementation. And eventually, when this rule is called at the end, then it's going to pop this, pop this, pop this upon the stack. It's going to elect each of them as children of this, create this subtree, and then push it onto this to the stack. So let's see how it goes in the actual processing of this. Now here I have my parse tree. So what I did is I took the parse tree here and I somehow represented the fact that as I'm traversing this tree here, as the parser is traversing this tree, eventually it's going to come, for example, let ID. So you have let ID v1. So you're going to be let ID, and then when it comes back here, it's going to have to execute v1. So what's on the top here of my arrows here is what is executed before I actually come to ID, if there is. Whereas if I have things that are to the right of my arrows, these are things that are executed after when I come back here. For example, I go let ID, and then I execute v1. Then I go back, let type integer, and then I call T, which is creating my integer node. Then I come back here, and then I go and then A2, and then A2, and then eventually I am creating the A3 node here, and then the V2 node here. And of course, here, as I come here, I forgot to say that, as I come here, before here, I actually come inside here, I have my A1 rule here. What is A1 doing? It's actually pushing my marker, my epsilon marker onto the stack. When I come here, I push my marker and push all the nodes that represents the sizes, and then execute A3, which is then doing the pop until epsilon, and then pops this, and then comes onto the epsilon. Then I go back and come here and execute V2, which is doing pop, 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 which is getting this, and then this subtree here, and then basically returning or pushing the entire tree of this sub grammar onto the stack. So you see that first thing that happens that I push when I come onto V1 here, I push this node here that represents the variable name, the name of the variable. Then the next thing is I come across this T here, which is pushing the type of this variable V, which is integer. Then when I come here, then I push my epsilon node by executing the A1 that is actually here. Then when I actually come here, after I parse one of these here, because I'm here in type, then when I come here after parsing integer, which I'm doing here, then I'm actually pushing, creating a node for this integer, which is actually this one here. And I'm actually pushing it on top of the, but pushing the integer here. And then when I come here, I push the epsilon onto the stack. And then, yes, when I come here, I actually, when I finish parsing one of the int lit, then I'm going to be calling the A2, which is creating this integer literal, which represents the size, integer literal node, which represents the size of the first dimension, then push it onto the stack. Then I continue parsing, and once I get to the next one, integer literal again, then I create another node and I actually push it onto the stack. So you see that now what I have on top of my stack is variable name, type, then my marker, and then the size of the two sizes of the array, 2 and 3. eventually what I'm going to do when I come back here and I hit this A3 here, then I actually execute this rule here, which is popping until the epsilon node. Basically pop, pop, pop. And then it elects these two nodes here as the two children of this array size node that I'm creating here. So this here is popping these three nodes from the stack, creating this array size node, and then electing this node 4 and 5 as the children of the array size node. So here 4 and 5 actually represents this respectively 2 and 3 dimension size of my array. Now I have an array size node that has two children which contain 2 and 3. And then I actually push this tree or subtree that I just created on top of the stack. So now I have 1, 2, 6. So now I have V integer and then both of the size of my array below my array size node here onto the stack. Then once I finish parsing this array size here, when I come back here, then I have my V2 here. So when I come back here, before I come to the top of the tree, then I execute V2. V2 is doing pop, pop, pop. So it's popping 3 nodes from the stack. And then it's making each of these 3 nodes as children of the arrays of an array size node that I am, a variable declaration node that I'm actually creating. So create a variable declaration node, pop 3 times, and then elect each of these as the children, respectively, of this variable declaration node, create this subtree, and then push this node on top of the stack. So you see that as a result of this, I actually have now this subtree, or in this case, the tree that represents my variable declaration. Okay. So you see that, again, I capitulate here. What you need to do is to define what are the atomic semantic concepts that are related to this subgrammar, this part of the grammar. Define if there are some composite semantic concepts that there are in this grammar, and then define the semantic rules that you're going to use to create nodes that correspond to these atomic and composite semantic concepts, and then figure out where to insert these rules into your grammar. Okay. But generally speaking, when you insert your atomic concept rules, they're going to be inserted right after a certain terminal symbol has been encountered that corresponds to this atomic semantic concept. Whereas the insertion of the composite semantic concept, semantic rules, is going to be after you parse the last composite concept, composite semantic concept of this composite, the last subordinate concept of this composite semantic concept. Respectively, here after I finish parsing the array size, then I have a rule at the end that enables me to create the array size concept or AST or subtree. And then here, after I finish totally parsing a variable declaration, then I call my rule here that is creating the entire subtree. Of course, you need also to determine how many children each of your composite concepts have, which determines how many nodes that you will pop from the stack. If you have a list that can be of any size, you can rely on an epsilon node here as a marker to make sure that you stop popping from the stack. Okay, so that's the end of this example. Again, you see that this is heavily related to what you have to do in the project. What I actually suggest is that you try to make it work for example, for your variable declarations. So you don't have to do this in one shot. You can actually do it, for example, for the variable declarations, and you make your parser run, and then you observe what is the ASTs that it had generated, and if they were generated correctly. Then once you know that it works for a part of your grammar, then you can add other parts, so on and so forth. If you try to make everything at once, it's going to make it more and more likely, like exponentially likely, that you will have one or more mistakes that are going to be compounded, so that your stack is going to get corrupted and everything's going to go haywire. It's going to be hard to figure out where is the problem or the problems. Of course, the more you have problems, the more they compound with each other, the more it's difficult to figure out what is wrong. So you start with something simple and you observe it actually works. If it works, then you add more. Also, by starting something simple, such as the example I just gave, enables you to have a good feel as to how it should actually be constructed. Okay, another example is the infamous ID nest here. So here, this is where you can actually parse things like this, where you have A.B.C.D. Or in this case, I have actually included the indices or indexes. So you can have A.B and C.D. Okay. Example, this is assuming that B is an array that has one dimension, and then C is the index in the first dimension of B, right? So that allows you to have any number of ... and then each of the different IDs can actually be indexed by any number of dimensions, okay, or index in every number of dimensions. Now, if you parse, here, this is the grammar that corresponds to this. That's the transformed grammar that corresponds to this in the original grammar. So that's been, after the grammar has been, or this part of the grammar has been transformed to LL1, as you have done in assignment number 2. So if you, these are the rules that correspond to, that can actually generate a sequence like this. If you actually try to use these rules to generate this sequence here, it's going to generate this abstract syntax tree. So essentially, you have ID dot ID. So that's the A dot B, and then the C between the square brackets, and then the D here, and that's the end of the list here. Note that you can also have the empty list here. So if there's no endless C, for example, for A and D, then you would have the empty list here, right? Okay, so this is the parse tree that is generated by this. Now, you see here that there's plenty of things that we don't want, again, in this parse tree. Essentially, what we want to have is something more orderly, such as this AST here. So that this is essentially a dot node. This is the left operand of the dot, which is A, and the right operand of the dot is another dot subtree, where the left operand of this one is the B, and then C, which is the indice of the array, which is B. And then the right operand of this second dot is D. Okay, so that's A dot B C dot D, right? So that's what you want to have, as opposed to this here, which has a lot of things that we want to eliminate. For example, each of these intermediate non-terminals here, and the epsilons, and the actual punctuation, and the parentheses, and so on, or brackets. We all want to remove that. That's information that's not necessary to have in order to convey the strict meaning of this actual expression or sub-expression. So that's the grammar. That's the parse tree that corresponds to this. And what we need to do again is to figure out what are the atomic concept and the composite concepts that are related to this grammar here. There is two kinds of atomic concepts. First is a name of a variable, which is these nodes here, A, B, and D. There is also yeah, so there is, well, two of them. There's one that is the first one, and there's one that is the second one here. Why do I make a difference between the two? You don't necessarily have to, but here I actually separated them. Arguably, you could have A instead of F here also. But depending on what's happening, if you want to make a difference between two nodes, depending on, that may seem to represent the same semantic concept, sometimes they may need to be differentiated depending on where, or use a different semantic rule depending on where they actually appear in the rules. Here, I actually chose to make them different just to show an example. Okay, so atomic concept, which is the first ID, atomic concept, which is the second ID, or the right operand after the dot, if there is one. And then another one is the epsilon, because I can have a list of indices. So I need, again, as I did in the first example, I'm going to actually use a epsilon node as a marker to push onto the stack to actually make myself stop when I want to get all the children of an ID if it has indices, because it can have any number of indices. So then this node would need to have such a number of children, which is variable. That's why I need to have, again, my epsilon node to mark the start of the list, so that when I will pop until I reach the marker, the epsilon marker. So that's where I have my push epsilon here, which is actually called here right before I start my indice repetition, which is inserting my nodes for my indexes, which are here. Now, why is this orange or yellow? Because eventually, inside of these square brackets, I could have an expression, which would open another whole part of the grammar. Here, essentially, I chose to simplify things and just say that for the simplicity of this example, I'm just going to consider that what's inside the square brackets is an ID. Okay. Eventually, it would have to be an expression subtree here, but here, for the simplicity of the example, I just basically assume that it's a simple ID. Okay. Which is what I have in my parsing sequence. The sequence of tokens that I'm parsing. Okay, so I have atomic concepts for the ID that is before the dot, the ID that is after the dot, and then the ID that is inside of my square brackets, which represents the index of a certain ID, if it is an array. And of course, I have my atomic concept for the marker that is the signification of the end of the list of indexes for a certain variable. Then I have to identify my composite semantic concepts. One is, let's start below the indice list here. My indice list is essentially what I'm going to have is a list of nodes that represent my list of indices for a certain variable. Right? So I'm going to have indice list node, and then below, what I'm going to have is the list of indexes for this particular variable. Potentially here, in this particular example here, I'm showing the epsilon node just to, because you could have it as a child also. You don't need to, but you could also have it as a child, okay? Just to show that it's also a possibility. Okay, so then, so that's it for my indice list composite concept. And then I have my var concept. So the var concept is that I have a certain variable which can have an indice list. So the variable here is B, and then the index is C. So that var actually has two subordinate concepts: the name of the variable and then the list of indices for this variable. And then the last one is the dot composite concept, which is essentially, it has two children, the left and the right operand of the dot operator. Example here, well, let's take this one here. This dot here is essentially B dot B, right? So that's all my composite concepts. So then I have my semantic rules for all the creation of all my atomic concepts and all my composite concepts. Now I need to figure out where to insert each of these semantic rules inside of my grammar. As I said before, the simple part is to take each of your atomic concept rules and then insert them at the right place. For example, right after you've parsed the first ID, you insert your semantic rule here after you've parsed the ID. After you parse the second ID, the right operand of the dot, then you insert your F rule here, which is creating this atomic concept, which is the right operand of your dot operator. And then the other one is as soon as you have parsed the expression, again, for simplicity here, I'm just assuming this is a simple ID, then you push, you put your rule here that is going to create this node, this leaf node in this case. If that would eventually be an entire expression, it would not be a leaf node, would be an entire subtree. But in this case, for simplicity, I put it as an ID. And then the last one is your epsilon here, which is the marker that you push before you start pushing all these indices in the indice list. Then where is this that you are starting to generate these indexes is before as you these indexes are parsed or generated as you are actually parsing indice repetition here. So before you actually start indice repetition, you actually call this rule here that is pushing your marker. So that when you come here, you push the marker, and then this indice repetition is basically going to insert all the nodes that represent each of the indexes. Then you need to insert the rules inside of your grammar corresponding to your composite semantic concepts. So for indice list, of course, the indice list is complete. So you insert a composite semantic rule or a rule that generates a semantic composite semantic concepts after this semantic concept has totally been parsed. Okay, so for example, for indice list, that's actually after you finish the indice repetition, you create this indice list subtree. So you insert the C rule here. And then for the var, when is it that you finish the var is actually also right after you finish the indice list. So it's possible that you don't have any indice list, in which case this C here the only thing that it's going to do is going to pop until epsilon, which is going to be the right thing, that the next thing that's on the stack, because there was no indice. Okay, in which case the variable is going to be created right away without having an indice list, or having an indice list that is empty. So the var node is created after you finish parsing this here. Then eventually the last one is the dot. So that when are you finished parsing an entire dot? Basically after you finished parsing this here. Then you finish parsing the dot ID and then the variable ID nest here. If you finish parsing this here, you have identified a dot subtree or entire tree. There are, again, I repeat, there are different ways to insert your semantic actions so that it actually works. Here I presented some kind of variation of another way to do things. You see that in the previous example, I have inserted my rules here at the end of the parsing. Example, variable declaration parses the entire variable declaration, and then I'm creating the variable declaration subtree, parsing array size here, and then after I'm finished here, I put my rule here that creates the array size concept, or semantic composite concept. Here I used a slightly different approach by inserting these rules inside of the rules. Okay. Traditionally speaking, you try to make them at the end of the rules, but you know, there's different ways to do this. There's no single correct way of doing it. Okay, I just included here variations so that you see that there are different ways to do this. Okay, so this is here my attribute grammar that corresponds to an AST generator that's been inserted inside of the right-hand side of my grammar. Now, again, what's going to happen here is that when I actually execute these rules here, as this parse tree is being traversed, then eventually, for example, when I go variable and then ID, after I parse the ID, when I come back here, I'm actually calling the A rule. Then I go to variable ID nest, and then I go indice repetition. This is epsilon here. And when I come as I'm coming in, when I'm coming in, I call the rule J. And then when I'm coming back, I call the rule C and D. And then when I go here, I go dot and then ID here. When I come after I parse the ID, then I actually use the F rule here, which is this one here. See, that's why I made the difference between A and F, so it's more clear that it's two different things. Then I will parse here, and as I come here, I will actually push my marker. And in this case, there is some indices or indexes, in which case this is here, there was actually no index. Okay. When I actually called the rule for processing my indice list for this here, it popped until epsilon, and then it was right away the epsilon node. That's why I don't have an indice list here that has some actual children. Okay. Okay, so when I go here, so when I actually come back here, when I call C, then it's going to actually pop until epsilon, and there will be this H node that is on top of the stack here. And then when I come here, and then I process D, which is going to create this var node here. Then by calling the var rule here. or the D rule that generates the var composite concept. Then when I come here, creating the ID here, that actually corresponds to my D here. And when I go here, then again, I'm going to try to process the list of indexes of D, which there is none. So it's going to basically insert the epsilon node here. And when I come back, I'm going to try to process the list, but the list is empty. I pop until epsilon. There's nothing to do there. So then I call D to generate this indice list, which is empty. And then the var concept by the D rule that's creating this entire subtree here. And then when I come back here, I'm actually creating the dot subtree here. And when I come back here, I'm creating the dot subtree here, right? Thus having the entire tree. So you see that here, it's showing you in what order these rules are actually taking effect. So that's basically the rule A, J, C, D, F, J, C, D, F, J, C, D, B, B, right? So that's what you need to figure out, in what order these rules need to be inserted inside of your right-hand side, so that their cumulative effect or the sequential effect is appearing in the right order, so that the tree is created correctly, right? So you see that the trace here is much longer because there's many more rules that are semantic rules that are triggered. So eventually here, it's going to be long, but here we go. So when I start, I actually come across A here. So I'm parsing the ID here. So I'm coming across A here. So I'm calling the A rule to create this leaf node, which is the left operand of my dot. And then I create this node and I push it onto the stack. Then I come here, variable ID nest. So I come here, J. So as soon as I get, before I get into indice rep, I call J here, which is, what is J doing? It's creating this epsilon node here and then pushing it onto the stack. Then here I'm processing the indice repetition here. The fact of the matter is that I don't have any indice after the A. So that returns back here, calls the C rule, which is trying to get all the indices from the stack by popping until epsilon. There's none. There's only the epsilon node. So it is actually making this epsilon node as a child of my indice list, which is the epsilon node that represents the list is empty. And so I popped my epsilon node, created this indice list node by way of the C rule here. And then I made this node as a child of this node here. And then I take this node here and I push it onto the stack. Now I have 1, 3, because this is here, 3. Again, I use numbers here to, make sure that we, and if you look at the tree here, for example, 1 is this here, 2 is this here, and then 3 is this one here, which I just pushed here, right? So at this point in time, what I have on top of the stack is 1, 3. So I have this node here, and then this subtree here onto the stack. Of course, the next thing that's going to happen is that I'm going to call the var rule here that is going to take this and this from the stack, create a var node, make this and this children of the var node, and then push this var node onto the stack. So that's what happens. The var rule here is called, it pops from the stack, then creates the var node, and then makes the 1 and 3 respectively the 2 children of the var node, and then pushes this var node onto the stack. Okay. So at this point, I have only this onto the stack when I actually come here. Then I continue parsing, and then I'm coming here. And then the next thing that happens is that I come across this ID here, which is here. So after I successfully parse this ID, I will come across this F here. That is essentially creating an ID node and then pushing it onto the stack. So that's my B here that I just pushed onto the stack, right? Then eventually I continue parsing, and then I get into my variable ID nest here. So that's where I come here. Then next thing happens is that I come across this J here, which is this one here. What J is, it pushes the epsilon because, hey, again, my B variable here could have some indexes, which it does in this case. So I push my marker onto the stack by way of executing the rule J. Then as I come here, then I successfully parse this whole expression here. Again, I make this more simple by making it an ID. Okay. If you would be parsing an expression, then you would go into an entire, possibly very complex tree here, and then creating the subtree for this expression, then coming back with the entire subtree that represents the entire expression. And that's what is the node that would actually be here on the stack, right? In this case, I just make it an ID for simplicity. So my ID node that I have here, or expression node, is the index of the first, in the first dimension of B. So I push it onto the stack by way of the rule H. Then I execute my C rule when I come here. So C, what it does is pops until epsilon. This is where we need to go to the next slide. So you pop, you're here, 6 and 7, and you pop until epsilon. So what is 6 and 7? 6 and 7 is my C and the epsilon. So it's actually, I pop 6, I pop 7, which is epsilon. I stop there and I make 6 and 7 children of the indice list node I'm creating here by the rule rule C. And then I actually push this node here on top of the stack, making this node 8 here being the on top of the stack. Okay. Okay, then, okay, the next thing is I'm going to call rule D here. Rule D is actually creating the var concept. So this var concept here has two subordinate concepts, which are the ones that are on top of the stack now, which is respectively the name of this variable and the list of indices, which is this node here. So I pop these two things from the stack, create my var node, and make 5 and 8 the respective children of the var node, and then I push it onto the stack. Then eventually what happens is that, so that's here, I'm here. So then I come to here, which is my D node in my parse tree. So after I successfully parse this here, then I'm still here after the ID here. So I'm calling F here. So I'm creating my D node here, and I'm pushing it onto the stack. Then I continue parsing, and then I go variable ID nest. Then because here I'm parsing the indice list. Before I parse the indice list, I push my epsilon marker onto the stack by rule J. So I push my epsilon marker here. Next slide. Of course, here what's happening is that I'm going to use this epsilon rule here. So there's no actual indice list, right? That's why when I go here, after I come back from processing the list, which was empty, when I call C here, C is going to pop until epsilon. And of course, what I have on top of the stack is the epsilon. So there was no list. Essentially, I'm creating an NDC list node, and whose only child is going to be an epsilon node to notify, to represent that this NDC list is empty. So pop the epsilon from the stack, make it the child of NDC list, and then push the NDC list onto the stack. Then next thing is going to happen is I'm going to call the D rule here. So the D rule is popping two things from the stack, the name of the variable and the NDC list, and then making the variable NDC list children of the var node, and then push the var node onto the stack. So what I have now is a var node onto the stack, which represents the right operand of my dot. In fact, now what I have on top of my stack is the left and right operand of the last dot operation in the list of dot operations in my sub-expression. So that's why when I come to B here, after processing this variable ID nest here, I call the B rule. The B rule is popping two things from the stack, which are the two operands of the dot, which are the node 9 and 13, and make this node 9 and 13 the two children of the dot node, and then push the dot node onto the stack. So now what I have is this entire subtree here that's pushed onto the stack. And at the bottom here, remember that we have this subtree here. Essentially what we have on top of the stack here is the left and right operand of this last dot that we are processing. And that's precisely what's going to happen. We're going to come back to the final B here, because this variable ID nest tail here was called twice. Tail here and tail here was called twice because it is an iteration. So now we come back to the first iteration's variable ID nest here as we come back in the tree here. So we call B again, which is B is popping two nodes from the stack, the left and right operand of the dot node, which are this subtree and this subtree here, creating a new dot node, making this the left operand and this the the right operand, and then push the dot node onto the stack. So that's it for that. So again, I'm doing a final recapitulation here of what you need to do, just so that it's clear. So you have your original grammar, which is the grammar that you transform into LL1. Then when you parse using this grammar, it's generating a parse tree like this. Figuratively, when you execute your parser, it is doing a parse tree like this. What you need to do is to figure out what are the atomic semantic concepts and composite semantic concepts that are present in these rules. Create some semantic actions that are eventually going to create the leaf nodes that correspond to the atomic semantic concepts, and then create other rules that are going to aggregate these atomic semantic concepts by creating a supernode, a parent node, and then elect some of the other nodes that you created before as children of this parent node that you're creating, and then you will push this parent node onto the stack. Okay. So identify atomic semantic concepts, create semantic rules that create leaves. Identify the composite semantic concepts, create other semantic nodes that are popping nodes from the stack, creating a subtree node, and then making these things that were popped from the stack as children of this new composite semantic concept. And you need to figure out where you will insert each of these rules inside of your grammar. For the atomic concepts, the rules are appearing right after a certain terminal symbol that corresponds to this atomic concept has been parsed. For the composite semantic concepts rules, they're generally speaking inserted at the end when the entire composite semantic concept has been finished parsing. Now, one thing that you may have been wondering, if you're doing the top-down table-driven parser, this is very clear that this is exactly what you need to do. Of course, if you're doing the recursive descent predictive parser, you might be like, that's not exactly how my thing works. So how is this attribute grammar helping me to figure out how to do the implementation? Well, again, figuratively, remember that even though it seems to be very different, both of these kinds of parser are operating in exactly the same way. So, figuratively speaking, as you're executing your, if you have a recursive descent predictive parser, you literally, in your parsing function for variable declaration, you parse let, you parse ID, you parse semicolon, you call the function type, and then you call the array size function, and you parse semicolon, right? Now, what you need to do is to create these semantic actions, which are functions that you create, and then you will insert a function call that is going to call each of these functions inside of the parsing procedure that each of your parsing functions are implementing. Of course, if you're doing the table-driven one, all you have to do is to create these symbols here, insert them in your right-hand sides, and then make it so that your parser is now able to deal with these semantic actions as they come on top of the stack, as I explained earlier in a previous video. So I hope this is going to be useful to you as you are actually doing your work for the AST generation. Thank you.